When people first start learning Python, they usually treat it like studying Spanish or French. They spend hours staring at flashcards, trying to memorize the vocabulary of the syntax and the strict grammar of the loops. This language-first mindset explains the high failure rate among beginners. It misses the actual task of advanced programming, replicating the way the human brain processes information inside a digital machine. Seasoned developers build digital mirrors of human psychology, creating structural hierarchies that sort, filter, and categorize the world exactly the way we do. Mastering code requires an understanding of human architecture. The syntax is simply the tool we use to implement it. In psychology, humans navigate a chaotic physical world using mental blueprints called schemas. When you encounter something new, you don't analyze every single detail from scratch. Your brain pulls up a pre-existing framework to instantly organize the mess. This prevents cognitive overload. If someone mentions a bird, you don't have to consciously deduce what a bird is. Your mental schema immediately generates a template. It has feathers, it has wings, and it flies. This animated diagram shows object-oriented programming utilizing that psychological system. Left, our biological bird schema. Right, its digital equivalent, a class. It establishes universal parameters, like feathers equal true, and a movement method, flying. Both human intellect and computers rely on these templates to execute efficiently. If the physical world was perfectly uniform, programming would simply be the act of stamping out these predictable templates to categorize predictable data. But nature is chaotic, and the environment inevitably presents an anomaly that shatters the template. A child goes to the zoo, looking into freezing water. They observe an animal with a beak, eggs, and feathers. But instead of taking to the sky, it is aggressively swimming under a thick sheet of ice. Why doesn't the child's brain completely freeze and throw a cognitive error? The new physical evidence directly contradicts the established mental blueprint. The true power of a system, whether mental or digital, is measured by how elegantly it processes unexpected anomalies. The human mind resolves the penguin paradox by generating a subcategory. It inherits the baseline rules for a bird, but modifies the conflicting physical behavior to accommodate the reality of the water. In Python, we execute this exact adaptive psychological process through inheritance and polymorphism. Instead of starting from scratch, we build a penguin subclass branching off the main bird class. Through inheritance, it automatically receives core attributes like feathers equal true. Then Python applies polymorphism to override the original movement method, changing the behavior from flying to swimming. This override mechanism allows the software to alter its behavior locally, executing the new instructions without destroying the architectural integrity of the original blueprint. By letting subclasses share the same method name but execute differently, we build dynamic systems that bend to new realities instead of breaking against them. When we pull back from the code itself, we see that building this adaptive architecture requires a specific human trait. This trait is cognitive flexibility, the ability to detach from rote syntax and adapt to structural shifts. Because software environments change so rapidly, this mental agility is the core skill engineering managers screen for in new hires. A sudden change in project scope or a massive unpredictable bug hitting the server is exactly the same as the child encountering the penguin at the zoo. It is an anomaly that defies the established plan. Rigid thinkers who rely solely on memorized rules fail in these moments. The reality in front of them no longer matches the instructions they memorized, but a dynamic engineer accepts the anomaly. They process the new context and architect a tailored polymorphic solution that keeps the project moving forward. The code we write is a direct reflection of our minds. Writing resilient software requires us to cultivate a resilient, adaptable intellect.